Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 4.6, day 2, entitled Modeling with Exponential and Logarithmic Functions. And today we're just going to talk about Newton's law of cooling and logarithmic scales. And these are two more applications of exponential and logarithmic equations. And Newton's law of cooling states that the rate at which an object cools is proportional to the temperature difference between the objects and its surroundings, provided that the temperature difference is not too large, of course. And using a little bit of calculus, Newton came up with his equation for the law of cooling, which is down here in this little box. And we have T of T, so that's going to be our final temperature after a certain amount of time. T sub 0, that's going to be the temperature of the surroundings. And then we have D sub 0, that's going to be the temperature difference. And then we have E, and then negative KT. K is going to be a constant, and T is going to be time. Okay, so we're going to apply this in example 7. Example 7 has D parts to it. So here's part A. We have a cup of coffee that has a temperature of 200 degrees, and it's placed in a room that has a temperature of 70 degrees. So we need D sub 0 eventually. That's the temperature difference between the surroundings and the actual object. So 270, that's a difference of 130. So we'll need that in a moment. Okay, 200 minus 70 is 130. So after 10 minutes, the temperature of the coffee is 150. So find a function that models the temperature of the coffee at a given time. Okay, so they actually give us a lot of information, and basically what we're going to find in order to write the model is the constant. That's what we need. Because they gave us a temperature after a certain amount of time. Remember, our original equation started with T of T. That temperature after a certain amount of time is 150. And then we had T sub S, that was our surrounding temperature. Okay, so that's the temperature of the room that it's placed in, the surroundings. So that's 70. They gave us that. Then we have D sub 0, that's the difference in the temperature of the surroundings and the coffee. So that's 130. And then we have E, but we don't have our constant. And then time, they actually gave us time. After 10 minutes, they told us we have a temperature of 150. So they gave us the information to find K, so that we can rewrite an equation that can be used for any room that's 70 degrees and any cup of coffee that's 200 degrees. Okay, so we have to do a little bit of work here for this one before we just get our equation and our function. So I'm going to substitute our information in, negative k times 10. And then we're going to have to solve for k. So the first thing I need to do is get rid of that 70, so I'll subtract it over. And I'm going to write this negative 10k just so it's not as awkward. Then I'm going to have to divide by the 130. I have to get that out of there because I have to isolate the e so that I can take the natural log of it. So I get 0.6154 when I divide those. So now I'm going to have to take the natural log of both sides. And when I do that, that's going to cancel out the e. So now I have the natural log of 0.6154 is equal to negative 10k. And now I can divide by negative 10. So now on my calculator, I have to do the natural log of 0.6154, get an answer, then divide by negative 10. So my constant is going to be 0.04855. Phew! So now I can actually write my equation. So I'll have 70 is the surrounding temperature. The difference between them is 130, and then I'll have e to the negative 0.04855 t. So if you have a cup of coffee that's 200 degrees and you have a room that's 70 degrees, that's the equation that you can use to find the temperature of the coffee at any amount of time. Okay, so in your homework tonight, you might have to do that. You might have to do a little more work today to get some of these equations. Yesterday it was a little bit easier with just some straightforward substitution. This is a little bit more involved. But now that we have that, part B is going to be really super duper easy. Find the temperature of the coffee after 15 minutes. So we're going to find T of 15, and we're going to use that equation that we had in part A. So we'll have 70 plus 130 e to the negative 0.04855, and then T is 15. So you're going to take 15 times the negative 0.04855, get an answer. Do e to that power, get an answer. Multiply by 30, get that answer, and then add the 70. Do not add the 70 and the 30 together. That's a common mistake. You're not following order of operations if you do that. You should get about 132.76, which is about 133 degrees Fahrenheit. So after 15 minutes, your coffee is going to be 133 degrees. Yikes, that's still hot. Okay, and then part C, when will the coffee have cooled to 100 degrees? So now we're finding the time. So now we're going backwards from what we just did in part B. So I'm going to put the 100 in for my T of T. I still have the 70, I still have the 130, and the negative 0.04855, but now I'm going to be solving for T. So again, like we did in part A, to solve for T, I have to subtract the 70 over, and then I'm going to have to divide by the 130, so 0.2308, so 30 divided by the 130. And then to get rid of the e, I've got to take the natural log of both sides. So then I'll finish it up here. So now I have the natural log of 0.2308 is equal to negative 0.04855t. So to solve for t, I've got to divide, oops, negative 0.04855. Phew! So take the natural log of 0.2308, get an answer, then divide that by our constant, and you should get about 30.2. So that would be after about 30 minutes. So again, if you wanted to write that as a complete sentence, you'd say after 30 minutes, the coffee will be 100 degrees Fahrenheit. Okay, and then part D says to illustrate this in a graph. So you would definitely want to do this on your graphing calculator. You'd go to your graphing calculator, you'd put in the original function that we had in part A, the one that has the value for the constant, and you have to use x in your calculator instead of t. So you have to go to y equals, type in 70 plus 130 times e to the negative 0.04855x in your calculator. Okay. And in your calculator, you might have to put that stuff in parentheses. Okay. And then when you graph it, you're going to have to adjust your window. Okay. We found a value of, let's see, what was it? After 30 minutes, the temperature was 100. So after 30 minutes, our temperature was 100. We also found that after 15 minutes, the temperature was 133. Okay, at 0 minutes, your temperature is 200. Okay, so when you're making your graph, you want to make sure those values show up. So when you're making your window, you want to make sure that you're going to be able to see 200 on the y-axis. So maybe make it a little bit bigger than that. Make it 225 for your y max, your x min, and your x max, or x min and y min, sorry. They can both be 0. It doesn't make sense to have negative time or negative temperatures on the coffee. Um, and then your y max, we said should probably be just a little bit bigger than 200, just so you can see. So make it about 225. Okay. And then for your x max, um, you're gonna have, you're not going to have a vertical asymptote, but you are gonna have a horizontal one. So for your x max, I mean, that's just how much time you want to go out. So I would go maybe to at least 30 minutes. I mean, our max value was 30. Um, you might want to go maybe 60, do an hour. Okay. But the temperature of the room, remember, was 70. So your coffee, as time goes by, will reach that temperature and stop. It'll plateau. It's not going to get any colder than that unless you put ice cubes in it, and that's not happening. So you're also going to have a horizontal asymptote of 70. Okay, so when you put that all into your graphing calculator and you graph, this is what it should look like, something like this. Okay, so your graph should start at 200 and it should approach 70 but never actually get to it. Okay, now as more and more time goes by, it will look like it's plateauing at 70. Here they just went the first 40 minutes, so even at 40 minutes, it's not quite at 70 degrees. Okay, so again, use those skills, write down a couple values. If you want to go in 10-minute increments, that's fine, but make sure that you make a table of values. You'd have T and then T of T. So that's what I want to see in homework and on quizzes and tests, and write down some of those values and then make your graph. Okay, logarithmic scales. There's two applications here, two or three actually, and they all have to do with um, different situations, like the pH scale that measures acidity, the Richter scale for earthquakes, decibel scales for loudness. Okay, so there's all kinds of applications here of logarithms and things that are easier to count in logarithmic scales because they have more manageable numbers. That's why we have these logarithmic scales. Okay, so one of our first applications is the pH scale, and this is how chemists measure acidity. And it was discovered by this guy Sorensen, and he came up with this measurement. The pH, whatever the pH of your solution is going to be equal to the negative log of H plus. So H plus is the concentration of hydrogen ions in moles per liter. Okay, and again, he did this so he could avoid very small numbers and negative exponents. So he wanted stuff to be more user-friendly. So if your ion concentration is 10 to the negative 4, then you just plug that into the equation. Now notice that when it's written this way, 10 to the negative 4, that base 10, the log base 10, and the 10 on this power, they're going to cancel. And then this little negative 4 is going to drop down. So you're going to have a negative 4, which is 4. Look at that. No decimals, no negative exponents. Very nice, user-friendly. So your final answer is very usable. And we have to remember that anything with a pH of less than 7 is going to be considered acidic. Anything with a pH greater than 7 is going to be basic. So you might see some problems where they want you to determine if something is acidic or basic. So remember 7 is the cutoff. Okay. So let's take a look at example 8 here. We've got part A and B. Part A says the hydrogen ion concentration of a sample of human blood was measured to be 3.6 times 10 to the negative 8th moles. So find the pH and then classify the blood as acidic or basic. So again, we need to remember that 7 is the cutoff there for that classification. So our equation then was pH is going to be equal to the negative log of our hydrogen ion concentration. Okay, so we have negative log, and they told us our hydrogen ion concentration here was 3.16 times 10 to the negative 8. Now, if you want to write this out as a decimal, that's probably going to be a little bit more convenient to put in your calculator. I know you can put the scientific notation in your calculator like that, but it would be 1, 2, 3, 4, 5, 6, 7 zeros, and then a 3, 1, 6 if you wanted to write it out as a decimal. Okay? So then it's just a calculator problem. You have to do negative log of that decimal. And you should get 7.5. And that means that it's greater than 7, so we're going to have basic, which I think is good. I don't think you want your blood to be acidic. Okay. And then for part B, the most acidic rainfall ever measured occurred in Scotland in 1974. It had a pH of 2.4. So we want to find the hydrogen ion concentration because that's what makes it acidic. Okay, so now we're going to be solving for H plus. Okay, so our pH was 2.4. Okay, so before we just take this original equation and start plugging information in, I'm going to rework this equation just a little bit so that we can isolate H plus. Okay, so if we have our pH and then negative log of the H plus, okay, if I want to try and solve that for H, I'm going to have to get rid of that negative 1. So I'm going to divide both sides by negative 1. Okay. Now remember, this is log base 10 if it's just log. Okay. So really, if we do our little circle method, we could write this as an exponent then. We could do 10 to the pH, or to the negative pH, equals H plus. So now that I have the equation in a little bit more user-friendly form, I can just substitute now. If I'm trying to find the hydrogen ion concentration, I've just reworked my formula using what we know about logarithmic and exponential equations, and now I can just do 10 to the negative 2.4. And that'll get me 0.003981. And I probably want to rewrite that in scientific notation, so we'd have 3.981 times 10 to the negative 3. And if you wanted to round that, so you had whole numbers, you could. You could say it's 4 times 10 to the negative 3, but this is fine. Usually for scientific notation, we like all those decimals. Okay. For our second application here, we have the Richter scale, and this was devised by Charles Richter, who was a geologist, and he measured lots and lots of earthquakes. And he came up with this formula, and he said that the magnitude of the earthquake is equal to the log of the intensity divided by the standard earthquake intensity. So, um, the largest magnitude we've ever had is 8.9. The smallest magnitude is 0, obviously. Okay. So then their ratio of intensities is 800 million. Yikes. Or billion. No, million. Okay, million. Okay. So basically, this just says that we're multiplying by a magnitude of 10. So an earthquake of magnitude 6 is 10 times stronger than an earthquake of magnitude 5. Okay, so each level goes up by a different magnitude, okay, different scale, different ratio. So using his formula then, we don't really have to completely understand how much the magnitude scale is changing. We just need to know that for this situation, in 1906 in San Francisco, there was an earthquake of an 8.3 on the Richter scale. And then in the same year, there's another earthquake in Colombia, or on the Colombia-Ecuador border, and it was 4 times as intense. So what was the magnitude of the Colombia-Ecuador earthquake on the Richter scale? So we have his equation that the magnitude is the log of the intensity over the standard intensity. Okay. Now here's how we have to work through this problem, because they don't really give us a whole lot of information that we can use quite yet. He gives us the measurements for the San Francisco, so he gives us I over S, or even log of I over S for San Francisco, which is going to be 8.3. Okay, but we have to modify this just a little bit because the Colombian one was 4 times as intense. So here's how we're going to modify this. If my intensity was originally I, the other one is going to be 4 times as intense. So I've got a 4 in there then for the Colombian one. And when we're dealing with multiplication, remember we can take combined logarithms and we can expand them out into 2 separate ones. So that's what we're going to do here then. So I'm going to have log of 4 plus log of I over S. So then this log of I over S, that's our San Francisco earthquake. So now I have log of 4 plus 8.3. So in my calculator then, I can do the log of 4, get an answer, add 8.3, and you should get 8.9 was the magnitude of that earthquake on the Colombia-Ecuador border. Okay, so once you see that little application of how you get that 4 times as intense into the formula, which is really just multiplying the intensity by 4, and then remembering that you can separate logarithms out. You can expand them into 2 little, one combined one into 2 smaller ones. So you make that log of 4 separate, and then that magnitude that they gave us, the log of I divided by S, okay, that's what he gave us for San Francisco. That is its own number that we can just substitute in. Okay, last example then is with the decibel scale. And this talks about how we're measuring the intensity of sound, and that initial intensity is right here. It's 10 to the negative 12, and that's watts per square meter. Okay, and so that's how we measure sound that's just audible. It's called the threshold of hearing. So that would be a really quiet intensity. I mean, obviously that's a really big decimal if it's 10 to the negative 12. Okay, so our psychological sensation of loudness varies with the logarithm of intensity. so that the intensity level is measured in decibels according to this equation. So we're going to take 10 times the log of the intensity and the initial intensity. Okay? And this I sub 0 right here, that's what they gave us up above. That's 10 to the negative 12. Okay, so the intensity level is B, and then I. Did they ever actually tell us what I is? I think that's just the intensity. Okay, so for example 11, we're going to find the decibel level. Oh, I'm sorry, find the decibel intensity. So we're going to find B of a jet engine during takeoff if the intensity, that's going to be the I, is measured at 100. And what was the Wm squared? That was watts per square meter. Okay. So this right here, this intensity, that's going to be the I that we were starting with. And then the decibel intensity there, that's going to be B, or the decibel intensity level is going to be B. So we have our equation. We have 10 log I over I sub 0. And we're solving for B. And we're going to have 10 times the log of, now they told us I is going to be 100. And then our I sub 0 is 10 to the negative 12. That was on the previous slide, that information they gave us. Now to simplify this, I'm going to rewrite it just a little bit because I have 10 to a power here. And I can make 100 into 10 to a power. So I'm going to have 10 times the log of 10 squared, because 10 squared is 100, over 10 to the negative 12. And now I have two powers that I'm dividing. And when the bases are the same, you subtract the exponents in order to divide the powers. So this is really 10 times the log of 10 to the, now it would be 2 minus a negative 12. So that's going to be 14. Minus a negative is plus a positive. So 2 plus 12 is 14. Now here, remember, this log, if they don't write in the base, remember it's just log base 10. So I have the base on my logarithm and the base on my power that are the same. So that log and that 10 are going to cancel. And then this 14 is going to drop down. So now I have 10 times 14, which is 140 decibels. So that's how loud a jet engine is during takeoff. Well, that's the decibel level of it. Okay. So when you're dealing with these homework problems, again, they're very short. There's only 4 of them. Definitely make reference to the formulas in your book. You're going to be applying a lot of very specific formulas, and use these examples as a guide so you can be conscientious of some of the, I guess, tricks, or maybe the more sophisticated methods to apply them. And if you have any questions, remember the problems are all worked out in the binder in the classroom, or you can stop by and see me before school.